So the shield goes north, and the web is going west. And they're going to collide. They'll get stuck together because the web is sticky, and the union of them, it's probably going to go somewhere in between north and west, and that's what we have to find out. So I'm going to call this resultant the V prime. No subscripts there because they're stuck together, so they're both going to have the same velocity. So I can just use V prime. The original ones, so I'll say I'll use A for the shield. I'll use B for the web. So VA was 20 meters per second, and it was north, as represented by the arrow. And VB was originally 25 meters per second, and west, represented by the arrow as well. The masses were given, so the mass of the web, MB, is 1.6 kilograms. And the mass of the shield is 5.4 kilograms. Okay, so it looks like we have a lot of the information here. So what I'll say is momentum before, the total momentum before equals the total momentum after. So I put a prime. That's true no matter how many dimensions we have. That's always true. This is a two-dimensional question, though. In this situation, the total momentum before will be the momentum of the shield plus the momentum of the web. That's before they collide. And momentum after is going to be, I'm just going to leave it as total for now. They get stuck together, so I'm just going to leave it as total. So the left side of the equation, the momentum of the shield will be the mass times velocity of the shield. So that'll be 5.4 kilograms times 20 meters per second. And that's going to be in Nauru's, and that's north. While the web, so plus the momentum of the web, that'll be the mass of the web, which is 1.6 kilograms, times the velocity of the web, which will be 25 meters per second. Multiply those together, and that'll be in Nauru's, but this one is west. And that's going to equal the total momentum of the resultant, which is going to be the total mass. So that'll be the total mass. I add those together, 5.4 kilograms plus 1.6 kilograms is 7 kilograms, times the velocity, which we have to solve for. Okay, so these are in two dimensions here. I'm going to multiply to get each momentum, and I'm going to divide by 7 as well to isolate the velocity. So 5.4 times 20 divided by 7. So that'll be 15.43. I'll keep a couple extra digits. Nauru's north. And 1.6 times 25 divided by 7. So that's 5.71 Naru's. Oh, sorry, they're not Naru's anymore because I divided it by 7 kilograms. I did divide it by the mass already. So momentum units divided by mass units will just be velocity units. So that's meters per second north, and the other one is meters per second west. Okay, so that's going to be my final velocity. Well, the magnitude of it, at least. Well, no, both. To figure it out, I need to draw a triangle. I need to draw a triangle with 15.43 north. Followed by 5.71 west. And my resultant is going to be my answer. So I'm going to find the magnitude and the angle. Well, okay, so to find the magnitude, I'll use the Pythagorean theorem. So I'm coming up with 16 meters per second. And the angle, I'll use inverse tangent of opposite over adjacent. So 5.71 over 15.43. Every time I try to type tangent on the keyboard, I end up typing tang and just got to put that G in there. It's automatic for my fingers. Okay, so that's giving me 20 degrees. So the final velocity of these things as a final statement would be 16 meters per second north, 20 degrees west. So does that make sense? I mean, that's a bit slower than each of them were going individually. They're not actually slowing each other down because they're going against each other. They're perpendicular, so they're not actually going against each other. They're kind of deflecting each other, but they're going to slow down because now it's the total mass together, so it should be a bit slower.